This second video, I'm going to talk about one exercise which has been assigned to you in the homework. It's exercise 8 on section 2.3. So the question is like this. We have three vectors, u, v, and w, on the plane, so in v2, in other words, or r2, such that the sum of those three vectors vanishing, so the sum of those three vectors is vanishing, and the norm of the two first vectors, u and v, is 1. So in other words, we said that those vectors are unit vectors. Moreover, we assume some orthogonality between u and v according to the figures, which is just let's say recopied and paste from the book. Question: what is the norm of the third vector w? All right, so without loss of generality, as we always say, we can always assume that one of the vector is, let's say, defining the orientation of the axis. So in other words, the x-axis passes through the vector w. That point exactly where, let's say, the feet of those three arrows, of those three vectors, coincide is just the origin of the system. All right, so now we're going to write all those vectors in components, sorry. So what do we have? Well, I don't know much about the two first u and v, so I call them alpha 1, beta 1, alpha 2, and beta 2. That's the only thing I know so far. I could say that both alpha 1 and alpha 2 are negative, and beta 1 is positive because it's oriented like so. U is pointing upward while v is pointing downward. So both alpha 2 and beta 2 are indeed negative. All right. For the third vector, things are a little bit easier since this vector is supporting the x-axis. In other words, well, there is no component in the y direction, so this means that the vector w in this coordinate system writes the norm of w, because it's exactly the position of this point here. There's a distance between the origin of this point, and 0 in the second component. Now, what we're going to do is we're going to just simply formulate what does it mean that u plus v plus w equals 0. Let's look at the x-coordinate. If you look at the x-coordinate, it tells me, let's start, sorry, I take it back. I'm going to start with the y-coordinate. It tells me that 0 plus beta 1 plus beta 2 equals 0. So that's, first of all, this equation that we get. And now if we look at the first component, it tells me that w plus alpha 1 plus alpha 2 should be vanishing. That's just saying that u plus v plus w equals 0 in the first component, in other words. So that's the second equality we have in this line. All right, so what does these all things mean? First of all, from the first equality, this means that beta 1 and beta 2 are the same, but one is the opposite of the other, let's say. So same in absolute value, but they are opposite sign. Now, further, since both vector u and v are of norm 1, we can say that the sum of the square of beta 1 and alpha 1 equal 1, and coincide also with the sum of the square of alpha 2 and beta 2. Well, from this equality and this equality, we deduce obviously that the absolute value of alpha 1 coincide with the absolute value of alpha 2, and since they are alpha 1 and alpha 2 are the same side, they need to coincide. So alpha 1 and alpha 2 are the same, they are negative both. All right, so if you read the explanation I gave in this video, the 2 pages, you can stop the video at any time. So I'm inviting you to read what I've prepared here. However, I just realized that we can solve this problem. We can answer this question without this explanation, and let's say it makes the exercise a bit shorter. Let's look at that triangle here. That triangle is particular. It's first of all a right triangle because we have this right angle here, this 90 degrees or pi over 2 in gradient angle, sorry. Also, we know that U and V are the same length or the same magnitude or same norm. This means the same thing. Well, it means that not only it's an isosceles, not only it's a right triangle, but it's also an isosceles triangle. Let's compute the length of the hypotenuse of this triangle. Well, thanks to Pythagoras' theorem, it tells me that the square of this length is the sum of the square of those lengths, U and V, but they are of length 1. Which means therefore, this means therefore that this length in square is, the square of this length is 2. So therefore this distance is exactly square root of 2. But what is this thing? I claim that the distance between those 2 points is nothing else than beta 1, the coordinate, the y coordinate of this point, minus beta 2, the coordinate of that point. But since we know that beta 1 plus beta 2 equals 0, now if we say beta 1 minus beta 2, that simply means I'm taking 2 times beta 1, or 2 times beta 2 in absolute value. So this distance is nothing else than 2 times beta 1. Ah, yeah, but since this distance is equal to square root of 2, this means that beta 1 equals square root of 2 divided by 2. Right, so if beta 2 is equal to 1 over the square root of 2, this means that through, for example, this equality, you got alpha 1 square. Alpha 1 square is also equal to 1/2. In other words, what I'm saying is that if you look at this triangle yet again, the angle made between this angle and the vertical axis is exactly pi over 4. Same thing for this vector. Or if you look, in other words, at this small triangle, starting from this point, which I call later in the explanation, it's I call this point the point B. Well, if you look at this triangle, the angle between the vector u and the x-axis is also pi over 4. So what do we have? We have alpha 1 is equal to alpha 1 square is equal to 1/2. So this means that alpha 1 is equal to minus 1 divided by square root of 2. All right, so alpha 2 is the same as alpha 1, we know that. So this quantity is equal to minus 1 divided by square root of 2, minus 1 divided by square root of 2. This means simply that w, the norm of w, is equal to square root of 2. And that's precisely, actually, I come here to the same conclusion, except that here we have a minus sign going on alpha 1 and alpha 2. Again, I need to apologize for this. We have square root of 2 equal minus alpha 1 minus alpha 2. But this is definitively the same answer. The norm of w is equal to square root of 2. All right, so this I've chosen this exercise, U and let's say 8 and 7, because I find out that these are mainly the most critical exercises in this section. Next, in the next video, I'm going to go back to the theory and explain you how do we define the dot product between vectors, even if I'm quite sure a lot of you already know what it means. So you will see, actually, I like to say it in advance, that in all the definition I'm going to give, most of the definition I'm going to give, we have an algebraic definition, but also a geometrical interpretation of the definition. Both, of course, coincide. I do not necessarily prove that they are equivalent all the time, but the proof in most of the time is not really hard. It's just taking a lot of time, that's all. But it's not really hard to see that those definitions eventually are the same. So I'm going to reserve the next video for the explanation of this dot product.